Hi everyone. So, since I have already mentioned in class announcement that the video which I have uploaded, those results will be used in your upcoming assignments. So, yeah, we should keep that in mind. And, let us solve the problems. So, the first problem is you have given a linear map from R3 to R2 like this. So, A of X, Y, Z is basically any way you want to write it, like a matrix or like a vector, I mean, like a tuple. It's your choice. So I may interchange in the between according to my convenience. Okay. So you have to determine which of the following sets forms the basis for the null space of A, right? So first of all, let us study what is the null space of A, and then we will use those equivalent criterias of basis. Okay, so let us compute what is null space of A. NaNulla, whatever the notation you want to. No one should cut your marks on notations. If some TA is doing, which I have heard, please inform us. We will take care of that. There are some TAs I know who are cutting marks on notation, so that should not happen. Okay. So this should be what? Zero. That's the definition of null space. All the points, vectors in domain which get mapped to zero by a operator. What is the zero there means? This is zero of R2. So this is 0 comma 0. Okay, well, what this implies guys, x, y, z, sorry, in R3, such that x plus y plus z is equals to 0, okay. Y minus z is equals to 0. Where these x, y, z are coming from? Definitely R. So you can write like this now, the set x comma y comma z such that x plus y plus z is equals to 0 and y is equals to z. Oh, well, I'm sorry, I forgot to write x, y, z in R. So it's amount to solve these equations in terms of like whatever dependency reducing the equations using row acting, but here it's not necessary if you see. So what is this? This is, so x is minus y minus z, and note that y is z. So z, z. So from here what you will get? Minus 2z. You can see. And then what you have? Z belongs to real numbers. That's all. So what is this? This is guys span of what? 2. Oh sorry, minus 2, 1, 1. Well, this implies dimension of null space is 1. The cardinality of the basis, right? And we have shown the cardinality of, like you can have different bases and the cardinality of all bases will be same. Why? Because we have shown it's the maximal linearly independent set. We have shown it is the minimal spanning set. We have shown something more also. Let's not worry about it right now. Okay, very nice. So what is your A part? So you have to see which one of these will give you a basis. So part A, the vector 1, 1, 1, vector minus 2, 1, 1. Can this be a basis? If it is a basis, if it is a basis, then what should be the cardinality of this? 1. Is it true? No. In fact, you observe this. What is A1, 1, 1? So A1, 1 is 1 plus 1 plus 1, comma 1 minus 1, that is 0. Well, this is not even contained in, your null space. So definitely it will not be a basis, right? Good. So two reasons I have given. Now you have another 0, 0, 0. Well, guys, if this is a definitely it's a null space, right? A of 0, 0, 0 is 0 comma 0. Is this a basis? So what is the span of this, guys? Span of 0 vector is always what? 0 vector. I mean, definitely it's not equal to span of minus 2, 1, 1, right? Because that vector only cannot be, you cannot expressed as any linear combination of vector 0, right? Because any scalar into 0 vector is 0. This fact we have proved in remedial classes. Okay, proper proof we have done. Nice. Let us do the C part. So we have to check if this thing is a basis or not. Minus 10, 5, 5. Let us first see if this even element, even this element is in a null space or not. So by definition, this is minus 10 plus 5 plus 5. Okay. And then this is 5 minus 5. Well, so this implies that this thing is in fact in null space of A. Okay. And note that we have proved this in remedial classes, or you might have done in class, or if you haven't done, do that. A non-zero singleton. This is a non-zero vector, right? So a non-zero singleton is always linearly independent. So minus 10, 5, 5 is linearly independent, independent subset of NA. What is the dimension of NA, guys? 1, right? So it's the maximal, right? What is the dimension? Dimension is cardinality of the basis. So it is the maximal, it is one of the maximal linearly independent set, right? So you can have different bases, no issues. So in fact, this is a basis. Yes, is a basis. Why? Because again, I'm repeating the reason. It's linearly independent and it's a maximal linear independent set also. Why? Because what is the dimension of this we have computed here? 1. So any linearly independent set the of dimension 1 will be a basis, because that's the equivalent criteria, right? B is a basis if and only if it is maximal linearly independent set, if and only if it is a minimal spanning set. Okay, very nice. And then let's do the D part. So, okay, minus 10, 5, 5, minus 3, 2, 1. Well, you can check this belongs to NA. This also belongs to NA. But is this a basis? So there are two ways. First, you see, um, okay, I think this way is better. So now, again, if it is a basis, right, then what should be the cardinality of this? Oh, by the way, no. My bad, I'm sorry. This does not belongs to null space, right? So the answer is much simple. So what is this? This is minus 3 plus 2 plus 1, 2 minus 1. Sorry. So this is 0 comma 1. So this is not equal to 0. So in fact, this is not even a subset of null space. So it cannot be a basis, right? At any cost. Basis has to be a subset of the vector space which you are looking, or the vector subspace which you are looking. Correct? So that's how the first problem is. Problem number 2. Now you have given that V span of these three vectors 7, 14, 0, 4, 8, 2, 1, 2, 1. Okay, guys. Now, what you have to do, you have to find a basis for this. It will be a basis if all these three, for example, all these three vectors become linearly independent, right? Or for example, one of them become linear independent or two of them become linearly independent. So it means, in other words, I already have a span, right? I have to just explore which of these vectors are linearly independent. So what does it mean to say equivalently? You have to check this. You have to look for the solution of such equations, right? 1, 2, 1 equal to 0, 0, 0. It amounts to solving three linear equations. So consider the augmented matrix of that. But it would be 7, 4, 1. You can check 0, 14, 8, 2, 0, 0, 2, 1, 0. Don't take the transpose. It will be problematic. So properly write the equations always and then do whatever you want to do. Okay. So this will be similar to what, guys? If let's make this 14 0. So R2 changes to R2 minus 2R1. Well, 7, 4, 1, 0. This becomes 0. This becomes 0. This also becomes 0. Right? And this is anyway 0. And here nothing we are doing. Okay. No, that's what you have, right? So this is your first pivotal element and this is your now second pivotal element because you have one row is 0. So what you get from here, guys? So you from here you get 2C2 plus C3 is 0. Okay. And what you get is, I mean, if you want to, simplify it further, you can do that to, simplify the calculations. 7C1 plus 4 um, C2 plus C3 is equals to 0. Okay, well, what this implies, let us see. So this implies C3 you can write as minus 2C2. Okay, so from the, first equation, what you will get, the second equation, what you will get 7C1 plus, or whatever, yeah, plus 4C2 minus 2C2 is equals to 0. So C1 is also equal to minus 2C2 by 7, something like this, right? Okay. By the way, yeah, what it means, you're getting one row 0, right? It means there is some, some dependency, right? Or there is a, let me think if it is a, there is another way what you can do. Maybe better to apply column operations and writing it in the some another fashion. But it's okay. Let us do like this only. So basically, what you get is, yeah. Let me copy this equation. I mean, I can quickly tell you the answer, but let me do it in more detail so you can do quickly once you learn the technique. Okay. So what you have here is, guys, this thing. So C1 is your, let's write it with the green color, okay, if you don't mind. minus 2 by 7 C2. Okay. And this you can write as something, something, something. What do you want to write? Tell me. Mm, where is? Oh, okay, this is C2 only. And this is minus 2 C2. Okay, that's what you have. Definitely. If you see, if you choose your C2 to be some non-zero, then definitely you see these, vectors are what? Linearly dependent, right? So these three are linearly dependent, right? So one row is becoming zero. It means like you have, how to say? But let me tell you a better way to do this. So a better way to do this is reduce it further. So I just make this above thing also zero. So 7, 0, 0. So operation will be R2 changes to, oh sorry, R1 changes to R1 minus 2R3. So this will be 0, 0, 2. And what will happen here, guys? So this will be, if you see this thing, so this will be 1 minus 2, 1 minus 2. This is minus 1, 1. That's all. Perform one more operation. So what you are seeing from here, this particular vector, the column, you can write as the linear combination of first two columns, right? So the third depends upon the first two columns. But first two columns are independent, right? So from here, what you can conclude is these first two vectors are linearly independent. And you can separately check also, like you can write this and all. So what the columns corresponding to these columns, what are the vectors? The 7, 14, 0, 14, 0, and another vector is 4, 8, 2, right? I mean, clearly is linearly independent. Because what you do in these, I have uploaded a special lecture if you remember. I think number one or number two, I don't remember. So in that special lecture, what we have done, we have seen that these row operations corresponds to a matrix multiplication, right? And those were invertible matrix. You can note that. So because of that, if you have at any stage few columns are independent, they will be independent. uh, you know, the actual vectors also will be independent because the row operation correspond to invertible matrix. You can here and there, multiply by inverse to get original vector. So this is linearly independent, but the third vector depends upon the first two, right? This clearly shows this first column. How you can multiply the first one by say minus 1 by 7 and this second vector by 1 by 2 and add them. That's all is the third column. So what is your basis? Basis it should be a linearly independent subset, right? So you have already span. So the basis for V will be, or our basis for V will be, this is not a unique choice. I will urge you to, find other choices also. 7, 14, 0, 4, 8, 2. So this is our basis, okay? So either you analyze like this, write the equations, and this clearly shows that one vector depends on another, then take the other two vectors and try to see if they're independent or independent. Like for example, if you just consider this thing, this first two vector what I was trying to do here is, this clearly says these three vectors are independent. So remove any one of them. So let's say you remove 3. Then again solve the system. Why? Because you have to check if C1, C2 are 0. You have already performed row operations. You know this will be like this. And from here, you will get C2 equal to 0 and C1 equal to 0. Or if you want to name B1 7 14 0 plus B2, you are confused with C1 C2. So essentially, I am doing this in that above shortcut. So this B2 you can see 0 and then B1 will be also 0. So it means these two are linearly independent. So the procedure is whenever you see a dependency, you drop at least one vector and see again if the others are linearly independent or dependent. You don't have to do the procedure again. You already have a matrix. Copy the, for example here, copy the same matrix and do the calculations for C1, C2, right? I hope you guys understood. Like, let me take one more example. So, for example, something 1, 1, 1, 2, 0, 1, 1, 1, 0, 0, 0, 1, 1. Something like this. I have to check, I have to find a basis for this. So let us first consider the C1 into V1. Let's call this V1, V2, V3, V4. So I am interested in, I already have a span, right? I need to check the conditions. When are these linearly independent or not, those kind of things, right? So what you have to do, you have to consider the system again. So 1, 1, 1, 2, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0. Now apply your row operations. You know how you do it. So this is your pivotal. 0, 0, 2, minus 2, minus 1, minus 1, minus 1, 1, 1, 0, oh sorry, 1, 0. I always tell you guys always perform one kind of operations, that is row operations. Don't go for column and all and confuse your life. I mean confuse yourself. So what is this matrix now? You know what row operations you have to perform. So let's say you make this down one. You want to make it 0. So you will multiply by 2 and add, subtract. So multiply by 2, so that is minus 2 and subtract plus 1. So what it is? Minus 1. Then again, multiply by, sorry, multiply by 2 and subtract 1. Okay, well, this is what you have, right? So you have this pivotal, this pivotal. So if you solve, what you get? C3 equal to C4 from this equation, meaning you have a dependency, right? So just delete one vector of any one vector of your choice. So it's a very natural thing, you know. You just imagine in your mind and just delete this vector. So if you don't have this vector, what you will get? C3 equal to 0, right? From the down one. Then from the second equation, so minus C3 equal to 0. And this from the second equation, if this vector is not there, minus 2 C2 minus C3 equal to 0. So this implies C2 is 0. Similarly, from the first equation, you will get C1 equal to 0. So when you deleted that vector, then C1 equal to C2 equal to C3 equal to 0 you have. So it means first three are linearly independent. So what will be a basis? So this is just a choice of basis. You can have different also. So this is a basis. I mean, why to just delete the last one? Maybe we can delete some other vector and try what happens. I hope you guys got the logic. Why I said just see the matrix and just see which all columns are linearly independent. So corresponding to those columns, the original column vectors will be linearly independent. That is the strategy. Okay, so question number 3. This is obvious. So you have given four vectors in R3. Why are these four vectors linearly independent? Let us see why. So let V1, V2. Of course, these vectors are different. Don't tell me that these are same. Otherwise, why we will call it 4. So what is R3, guys? This is X, Y, Z. X, comma, Y, comma, Z belongs to R3. Sorry, R. So let us find a basis of this to investigate what is its dimension and all and all. So what you can do is you can take X common, then Y common, and then Z common. This strategy I have taught you in um, the earlier assignments also. That's why I told you to do this way. But I am very sad none of you have written this way in exam. I told you always whenever you have to find span, write like this, but none of you listens properly, right? It's your bad. Like you have to practice now, which you should would have already done something before. Okay. Well, the dimension of R3 over R is 3. Very nice. So now, what is basis? Basis is maximal linearly independent set, right? So set of any set with more than 3 elements, can it be linearly dependent by those equivalent criterias? No, right? Is linearly dependent. So the four criterias which I have proved for you. Okay, this is about question number 3. Question number 4. So is it always true that V1? Okay, so let us see. So let V1, V2 are linearly dependent. So you have to check if there exists a lambda in R such that something happens. So this means there exists C1, C2, not all 0. Say C1 is non-zero, such that C1 V1 plus C2 V2 is equals to 0, right? So what this will imply, guys? This will imply C1 V1 is minus C2 V2. This will imply V1 is equals to minus C2 C1 V2. But you have asked if there exists a lambda in R such that what is your question? So you have to check the validity of this statement. Let me write the statement. Check if if V1 V2 are linearly dependent. So if and only if there exists lambda in R such that V2 is equals to lambda V1. Guys, note one thing. So we have something like this, right? Okay. So what if? So if you take these vectors, so this depends upon the condition that C1 is non-zero. Maybe C2 is 0, right? For example, right? If C2 is 0, so if C2 is 0, then you cannot express V2 in terms of V1, right? This is not possible. So this suggests you this statement is not valid, right? At least the forward side. So for example, if you take say V1 equal to, just a second, V1 equal to say 0, 0. Okay. And V2 you take 1, 1. So see, 0 into I'm sorry, 3 into V1 plus 0 into V2 is what? 0, right? So can you express V2 as some lambda times 0, 0? Never, right? So this statement is not true. That's what. You have to check the validity of that statement. Okay. Question number 5. This is a beautiful problem. You are given some vectors, 9 vectors in R9. And you have given that these vectors forms a basis for R9. And you are considering making a matrix column wise, 9 cross 9 matrix. Okay, VIs are columns. Can you explain why following cycle? So A part is AX equal to 0 has unique solution x equal to 0 in R9. What is your B part? For B in R9, AX equal to B always has a solution which is unique. See, this is by the result which I have proved. If you remember, I have proved this result. If B is a basis for V, or no need of if here, if and only if every element in V can be expressed as unique linear combination of vectors in D. So using this, like if you take any B in R, so for any B in R9, there exists, right, some C1, C2, dot 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 C9, such that what will happen, guys? Such that C1 into V1 plus dot 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 CA into Vn is B. Oh, which is same as and more. And CIs are unique. They cannot be like these are unique scalars, right? You cannot have different combinations because you have learned that it can be expressed uniquely as linear combination of vectors, right? That's what the statement is. And this I have proved for you. So this is nothing but this is just this, right? Sorry, this is not N, this is 9, my bad. B. So well, you have a unique solution. And you know, 0 you can express always as 0 into V1 plus 0 into V2. So plus dot 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 0 into V9. So X has to be 0 in this case, right? Okay. Now the next problem. Question 6. So you have, collection of all polynomials Px. I hope you know this vector space. We have defined it for you. P3 are the polynomials, of degree less than equal to 3 with real coefficients such that there is a condition P of 10 is 0. So if you see this is just the subset of P3R, you have to show this is a vector space over R. You know P3R is a vector space over R that you have proved. I have at least asked you to prove in remedial classes, and I have done many problems like that. We just have to prove this V is a vector space. Do we have to verify all those axioms? No. We just have to prove that it's a subspace. That's all, and we are done. Okay? So first thing, note one. What always you should check if 0 is there. So if you define P of x to be just a 0 polynomial, of degree less than equal to 3, what is P of 10? Oh, well, 0. So this implies Px, let's call this polynomial as this 0. Ah, so this implies, yeah, in fact, this 0 polynomial belongs to V. Note 2. Now you have to take two polynomials, P and Q in V. So what it implies, P of 10 is 0, Q of 10 is 0. Okay, let us see what this means. Let us expand this set properly. So it means all a0 plus a1x plus a2x square plus a3x cube, oh my god, such that p of 10 you have to put. So a0 plus 10a1 plus 100 x, sorry, 100 a3, a2 plus 1000 a3 equal to 0. That's what the condition is. So if you have two polynomials, let it like one is a naught plus a1x plus dot a 3x cube, and q is given by b naught plus b1x plus b2x square plus b3x cube, and you have given these equations. So what is p plus q of 10? That's all you have to verify. Well, I'm not doing it. You can check. This will be p of 10 plus q of 10 by definition. Well, these are 0. Okay, so this implies p plus q belongs to V. And similarly, I urge you guys to show that this also belongs to homework. We have done many problems like that. That's why I'm leaving for you now. Okay, well, so this is a vector space over R. What you have to find? You have to find a basis and compute its dimension. So let us, since I am lazy, I will copy. Oh no, let me do it again. So what is V, guys? This also I have told you, find a spanning set, these kind of questions you remember. We have done A2, sorry, 2, 3. So what is this? You have given A0 plus A1 into 10. My God, I don't like this number 10. A1 plus 10 square A2 plus 10 cube A3. I'm just saving my space. This is 0. And AIs belongs to where? Real numbers, right? For every I in 0, 1, 2, 3. So what you will get from here, guys, is you get A0, this whole weird quantity, right? So 10 A2, sorry, what is A0? Minus 10 A1, oh, minus 10 square A2, minus 10 cube A3, plus A1x, plus A2x square, plus A3x cube. Okay, where A1, A2, A3 belongs to R now, because A0 is gone. Now what you have to do, you have to take A1 common. So when you take A1 common, minus 10 plus x you will get. Then you have to take A2 common. So you will get x square minus 100. And then you have to take A3 common. Then you get x cube minus 1000. Very nice. So A1, A2, A3 are in R. Well, we get a spanning set, right? So this is span of x minus 10, comma, x square minus 100, comma, x cube minus 1000. What we have to do? We have to check among these which all vectors are linearly independent. So that also I have shown you how to check. So you will consider this linear combination, right? I have given you the logic. Two polynomials, when two polynomials are equal, when their coefficients are equal, right? I have given you the logic also. It comes from the derivative thing. So 0 into 1 plus x square plus 0 into, sorry, yeah, uh, 0 into what? Um, let's keep. So what you get from here is, guys, so collect the coefficients. So minus 10 C1, minus 100 C2, minus 1000 C3. This quantity will be 0, right? And as well as C1 will be 0, C2 will be 0, C3 will be also 0, right? You can compare the coefficients. Well, what it means, all Ci's are 0 if this linear combination is 0. That's what, right? So it means all the three vectors are linearly independent. So what is the choice of your basis? This is the choice of your basis. And what would be the dimension, cardinality of basis? That is 3. Well done. This is done, right? Okay. Question number 7. So you have given all matrices of order 3 cross 3 with real entries such that A transpose is minus A. Okay. You have to check if this is a subspace or not. Recall over R, of course. Subspace, I mean, you have to check vector space, but this is a subset of M3R, right? And M3R over R is a vector space. So that should be your logic. So you just have to check subspace. So note 1. Is 0 matrix there? What is the transpose of 0 matrix? 0 only, right? So 0 matrix belongs to B. Note 2. So it's non-empty. Let A comma B belong to B. So what it means, guys, A transpose is equals to A, B transpose equals to B. Let us see what is A plus B transpose. Now, A plus B transpose. So what is the entry of A plus B? You write general entry like this, right? And transpose you have to do. Transpose meaning rows become column, column become rows. This will become AJI, right? Plus BJI. Okay. And this will be the matrix AJI. You know how to add matrices again, that BJI. Well, this is what now? This is equal to, we know that this is what A transpose. This is what B transpose. And we know these are already equal. Well, A plus B transpose is A plus B. Right? Note 3. Note that I haven't used that it's a 3 cross 3 matrix. So it means you can do it for any n. Any n you can do. So that is your homework. I'm doing for, 3. So yeah. So what will be note 3? The scalar multiplication property. So what is alpha A transpose? So alpha now A. So this will implies A plus B belongs to B. That's what we wanted. So what it would be, guys, you know how to multiply a scalar. So you do with each and every entry, and then you're taking transpose. So this will be alpha AJI, right? Alpha is multiplied with everything. So again, you can take alpha common. What's the harm? Oh well. And what is A transpose? It is A, because A is in B. Oh, in fact, this is alpha A transpose is same as alpha A. What this means? Alpha A belongs to B. This implies B is a vector space over R. Field is very important, guys. I have given you some examples in remedial classes why field is important. And everything you are doing with scalars, you are expressing with the vectors, field is very important. Okay, so yeah, this is a vector space. And now you have to compute the dimension. So let us do a little bit of hard work. What does this mean, guys? This means Aij equal to Aji, right? So let us write it properly. So this is collection of A11, A22, A33, A12, A21, A23. Why I'm writing this only because I know these are equal. This will be A, something wrong, something wrong. This will be 1, 3, right? 1, 3. This is A13. This property for every ij. Okay? And oh, by the way, this is not question 7. This is question 8. What I'm doing. I mean, doesn't matter. It's fine. This will be A23. And then this A11, A12, A13, A22, A23, A33. This belongs to R. Now what you have to do? You have to take these elements common. So 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. I mean, I'm writing just directly. I'm taking common and not writing plus. What is this? So what will be? This will be span of. Oh, I'm pressing some button, I guess. Span of. Okay, I got it. What happened? You take A11 common, then you take A22 common, like that, or say A12, and then you take A13 common, everything you have to add. And then, write it. You have to write it. I'm very lazy in writing, so 0. See, A12 you have already taken, so then A22 you have to take. Then A23. No, no. What nonsense I'm doing? A13 I have taken? Yeah, in a wrong way. This should be there, right? And then you have to take A23, right? 1, 0, right? And then finally, yeah, 6 matrices you should have. Yeah. 1, 0, 0, 0, 0, 0, 0. Wow. So what happens now, guys? So you have to check if these are linearly independent or not. So consider a linear combination, let's call it V1, V2, V3, V4, V5, V6. And consider this 6V6 equal to 0. What is the 0 here? 0 matrix. And sir or ma'am, compute the coefficients. You will get all alphas are 0. So that's why I have properly chosen something how to write it as span. I had a purpose for asking you to do this always in your answers where whenever you are showing something subspace or something, something, something. Okay, well, what I was about to say. In fact, you can use that property also rather than proving it separately subspace. I have shown you that span of a set is always a subspace. So you can use that also. Okay, so these alphas are 0. It means these are linearly independent. So what is the dimension of this V? That is 6. So in general, if you have n, okay, then you can see that the dimension would be, mm, if you have, like, n cross n matrix, if you take this in MNR such that A transpose is A, you can check the dimension would be n square minus n by 2 plus n. So this is n square plus n by 2. I'm not proving it. This is your homework. Okay, so well, question 8. So question 8 is you have to, I flipped the order, but it's fine. You have again 3 cross 3 matrices, and so this is similar. I'm not showing that this is a vector space. That's what you have to show. Okay? And I will just analyze this matrix a little bit over R. So what does this means? Aij is same as minus A ji, where ij belongs to this 1, 2, 3. So if I equal to j, what you get, guys? Aii is same as minus Aii. Oh well, this implies Ai is 0. Oh wow, that's a fun thing happened here, right? Now, so what is V? V is in fact the collection of these kind of matrices. A1, 2, A1, 3, A2, 3. So this will be minus A1, 2. This will be, yeah. Minus A1, 3, minus A2, 3. So this matrix, right? Sorry for the bad orientation. Okay, I can write it better. Minus A2, 3, 0, right? A1, 2, A1, 3, A2, 3. This belongs to R. Now you know what you have to do. And you know the dimension also. You can directly say 3, right? And you know the bases also. 3 matrices. So in general, again, if you have in, there is your homework, and A transpose is minus A, show that dimension of V is n square minus n by 2. Is this fine? 3 to 3, 9, 9 minus 3, 6, 6 by 2. Yeah, it's fine. Okay, good. Now, let's go to the question number 9. So you have, now you are considering V to be span of all A in M3R such that A is invertible. So what can you say about this? Okay, we're considering span of all 3 cross 3 invertible matrices. Okay, what can you say about this? Is this a vector space? Yes, definitely it will be a vector space because it is span of some vectors. But what will be the dimension and how things will happen here, right? So that is what you have to, see. It's not, it's not a very simple problem. This, I forgot the notation. Um, yeah, I forgot the notation. There is some notation also for, these kind of things. Uh, yeah, I don't remember the notation. By the way, what will be the dimension of this M3R? You can check that it would be 3 crossed, that is 9. Show it. Okay? No. The thing is, you have to now observe what can you say about the dimension of this thing. So I think I can leave this as an exercise because this is a very, fun exercise to do. So yeah, I will leave this as an exercise. It's not hard. Or maybe let me show you something. Okay, let me do it. So let me think whether I should do or not right now. Yeah, why not? Yeah, yeah, I think I can leave this as an exercise. A in M3R such that A inverse exists. So what you have to do is if inverse of this matrix exists, you have this property that A into A inverse is identity. This is equal to A inverse into A. This will give rise to some equations. And these equations will involve these AIs, right? And note that dimension of, oh, sorry, this is not V, span, I'm sorry. Just span off. Then what you have to analyze is, you have to analyze like, yeah, and note that this dimension is 3 into 3, 9. Definitely, definitely you will have, um, the dimension of this vector space should be less than equal to 9, right? Because see, because V is contained in this M3R. This you will prove. I am not proving it, but you think like this. So what is the basis? Basis in V is the maximal linearly independent set in V. It is possible that maximal linearly independent set of M3 has more elements than in V, right? I hope you understood. So for example, if I give you something, say consider this matrix 1, 1, 1, 0, 0, 0. Consider this matrix minus 1, 1, 1, 0, 0, 0. No. Consider this matrix. Sorry. Yeah. So like this. So 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. No, okay, plus 1 maybe. Okay. Consider another matrix like this. Say 1. All these matrices what I'm writing are invertible. You can check. 1, and then you can have 1 here and say minus 1. So if you see these four matrices, I'm not solving this question fully because this is very interesting. So these four matrices are linearly independent. You can check. Okay. Or do you want me to check? I can also check. So if you do this, is call it A1, A2, A3, A4. So alpha 1, A1 plus alpha 2, A2 plus, or maybe these are not linearly independent, but let us see if they are. Yeah. So what I'm trying to say is find, I I'm not solving this. See what all possible, simple matrices you can have which are linearly independent. I have better examples also, but yeah, like maybe let me change, modify my examples, or let us see if they are linearly independent. Let us do some analysis. So what you will get from here is alpha 1 minus alpha 2 plus alpha 3 from the first entry minus plus alpha 3 plus alpha 4 is 0. From the second entry, what you will get? I mean, second as in this, all others are 0, right? So alpha 1 plus alpha 2 minus alpha 3 plus alpha 4 is 0. And then one more equation you will get. Alpha 1 plus alpha 2 plus alpha 3 minus alpha 4 equal to 0. Definitely, let's see. Let's solve these equations. So 1, I'm substituting in matrix and equating to a 0 matrix. You can get these equations. I'm not explaining how. Let us analyze a little bit. So 1 minus 1, 1, 1. Everything is 1, so nice. 0, 2, minus 2, 0, 0, minus 2, 2. Um, no, this is 0. This is 0. And this is minus 2, right? Yeah. This is plus 2. So 0, 0, 0. Simplify it a little bit. So what you get from here is if you just write like this, so 1 minus 1, 1, 1. So 0, 1 minus 1, 0, 0. I'm applying some row operations. You can see what row operations I'm applying. And then you have, well, what you can observe from here, not all four are linearly independent, but at least A1, A2, A3, right? Because if you delete this particular column, meaning it amounts to deleting this matrix A4, right? Then alpha 1 equal to alpha 2 equal to alpha 3 you will get. So these are linearly independent. So you got 3, right? So I will not solve this question, but try to look more matrices, simple matrices like this, okay, which are linearly independent. And say, I'm not saying if it is true or not, say that you got 9 matrices in this set which are linearly independent, okay? 9 invertible matrices which are linearly independent. So what would be the span of this? The span of this has to be equal to nothing but M3R only. So that would be so fun. So I'm not revealing the answer right now. Okay, let's do the final problem. So you have a matrix S such that S of E1 is E2, S of E2 is E3, and S of E3 is 0. Where E1, E2, E3 are standard bases, meaning E1 is 1, 0, 0 of R3. So S is 3 cross 3 matrix, of course. E3 is, or no, S can be anything. Let's see. We'll see. What do we want according to that? 0, 0, 1. Now, you have a set, I mean a vector space, all A such that Yeah, you have to multiply SA with AS. Like, yeah. So now this is what you have. So S has to be the 3 cross 3 matrix. Sorry, in M3R. This is what given to you. Okay? So what you have to do is you have to find basis and dimension. And first of all, prove this is a vector space. So let us do step by step. Let us first prove this. Let us first analyze what is S. Okay? S you can name like this. Say S11, S12, S21, S22. Oh, sorry. What the hell I'm doing? So this is called tiredness. So S13, S21, S22, S23, S31, S32, S33, right? So what you have given? You have given something, no? S of E1. What will be S of E1? You can compute, I'm not computing, multiply it by 100. So what you will get? S11, S21, S31, right? When you multiply it by 100. So yeah. So this is what you have given. This is E2, 0, 1, 0. So meaning you have given S11 is 0, S21 is 1, S31 is 0. Similarly, you check the other conditions what sir has given. You will get S12 is 0, S22 is 0, S32 is 1. And you will get S13 equal to S23 equal to S33 equal to 0. Now you see S has become, solve the other two equation. Now if you see, S has become a very simple matrix. So what is the matrix? I forgot. So I think 0, 1, 0, 0, 0, 1, 0, 0, 0. And you have to look all the matrix A such that S equal to AS. So let us analyze what is S equal to AS. Let us, understand the vector space better. So what is S? 0, 1, 0, 0, 0, 1, 0, 0, 0. Let's take your matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Let us multiply this first. SA I'm computing first. Yeah, so what you will get? A21. Then what you will get? A22. Then what you will get? A23. Then what you will get? A31, A32, A33. You can check. Then 0, 0, 0. Okay, let us multiply AS. So AS, this is SA. And what is AS? Right. This full. I'm not writing it. 0, 1, 0. Let's write it. Because then I will make definitely a mistake. A11, A12, A13, A21, A22, A23, A31, A32, A33. I am rushing because I have to attend a talk also. So what will we get now? 0. Areva, very nice. So why this was not happening there? Okay. Second element will come and then yeah. This with this 0. This with this A11. This with this A12. Then again 0. A21. No, something is wrong. So this with this, no, it's correct, it's correct. A, now what we will get is A21 and then A22 and then similarly 0, A31 and then A32. And SA is equals to AS. So what it will give you? A21 is 0, A22 is A11, A23 is A12, right? By first row. Then A31 is 0, A32 is A21, A33 is A22, and the last will give you A31 is 0, which is already we have. A32 is also 0. Now what you have to do? You have to club this all together. What is A11? Any condition on A11? Let's have A11. What is A12? Let's have A12 only. What is A13? Is it 0 or something? No condition, right? A21. Any condition on A21? Yeah, it is. Let's write like that only. A21. Any condition on A23? Yeah, A23 is A12. And A, no, it is A22. Any condition on A22? No condition on A22, right? No, A22 is A11. And then I have this A13, right? A23 condition is 1, 2. A31, see if there is any condition, yeah, it is 0. By the way, A21 is 0, right? I forgot to mention that. A21 is 0. And then what you have? A32. A32 is 0. A33 is A22. A22 is A11. Oh wow, this is what you are getting. This is your V. Now you know how to do. I may have made a calculation mistake. Please forgive me for that. You can, do the rest. It will be of dimension 3. You can check. You know the procedure, right? We have done in all other questions. So thank you very much.